Alright, let's hear more about the methods for determining whether a number is prime or not, the deterministic methods and non-deterministic or probabilistic methods. Okay, let's listen.
While the fundamental principle of generating large prime numbers for applications like cryptography still largely revolves around generating a random candidate and then testing its primality, research continues to explore more efficient and, in some cases, deterministic methods for finding these colossal numbers. However, for the very large primes typically discussed in the context of current cryptographic standards, thousands of bits long, the most widely used and practical methods remain rooted in probabilistic testing. Here's a breakdown of the latest approaches and the ongoing landscape. 1. Refinement of probabilistic methods, still dominant for practical generation. The core technique for generating large primes for practical use, such as in RSA and other public key crypto systems, continues to be: generate a random odd number of the desired bit length. Perform a series of probabilistic primality tests, most notably the Miller-Rabin test. While the fundamental Miller-Rabin algorithm has been around for some time, ongoing work focuses on optimizing implementations, making a modular arithmetic operations within the tests as fast as possible through clever algorithms and hardware acceleration, selecting optimal bases. For a given size of number, research continues to refine the set of bases used in the Miller-Rabin test to provide a high degree of certainty with a minimal number of iterations. Combining tests. Sometimes, a quick initial check using trial division by small primes or a Fermat test is performed before applying the more computationally intensive Miller-Rabin test. The Bailey PSW test is another powerful probabilistic test that combines a Fermat test with a strong pseudo-primality test and has no known counterexamples, composite numbers that pass it, up to a very large limit, making it highly reliable in practice. The emphasis here is on efficiency and achieving a cryptographically acceptable level of certainty rather than absolute deterministic proof for every generated prime. The probability of a composite number passing multiple rounds of a strong probabilistic test like Miller-Rabin is astronomically low, far below the probability of hardware errors, making it sufficient for practical security. 2. Advancements in deterministic methods, more theoretical or for proofs. While not typically used for the routine generation of large primes and applications due to their higher computational cost compared to probabilistic methods, deterministic tests continue to be an area of research. The AKS primality test. This remains a significant theoretical achievement as the first unconditional deterministic polynomial time primality test. While its initial complexity was high, there have been subsequent optimizations. However, it is still generally slower in practice for key generation than probabilistic methods. Its value lies in its
So we are going to take a look at the major primality test methods, the actual methods, the actual equations. So first one is of course trial division, which goes from 2 up to root over n. Of course for very large and it is not really acceptable. Then the Fermat primality test for random a, check if a to the power n minus 1 equals to 1 modulo n. So for instance n is 17. This is, by the way, this is also used in Shor's algorithm, right? So for n equals to 17, a equals to 2 times 2 to the power 16 modulo 17 equals to 1. So 17 passes this test. Some composites can do pass Fermat primality test. So this is a probabilistic test. For instance, Carmichael numbers can pass Fermat test. Then we have this Miller-Rabin primality test. So write n minus 1 equals to 2 power 8d, with where d is an odd number. For random a, check if a power d equals to 1 mod n, or add to the power twice rd is to minus 1 modulo n for some 0 less than equals to r less than equals to s. So it is kind of like an extension to Fermat's. Check if a power d equals to 1 modulo n. So example, n equals to 17, so a equals to 3, 17 minus 1 is 16 equals to the power 4 times 1. So there you have it. Or a to the power twice rd equals to minus 1 modulo n. So compute 3 to the power 1, c squared, 3 to the power 4, 3 to the power 8 modulo 17. widely used for large numbers. Then there is this Solovay-Strassen primality test. So here we have for random a, check if a power n minus 1 by 2 equals to a by 1 modulo n, where a by n is the Jacobi symbol. Then we have AKS primality test based on congruence. X minus a whole power n equals to x power n minus a modulo n x power r minus 1. So AKS is deterministic and polynomial time, but slow in practice for very large n. Then there is Lucas-Lemma test, elliptic curve primality probing. Then also there are softwares available.
Search for primes with specific structures. However, translating these theoretical findings into practical, fast algorithms for generating general large primes is an ongoing challenge. In summary, for the practical generation of the very large primes used in today's digital world, the state-of-the-art relies heavily on efficient probabilistic primality tests, primarily the Miller-Rabin test, applied to randomly generated large numbers. While deterministic methods and theoretical research continue to advance our understanding of primes and primality proving, they haven't yet supplanted the speed and practicality of well-vetted probabilistic techniques for the high-throughput generation of large probable primes required by applications like online security.
Alright, so there we have it.